Hi, I'm Mr. V. Today we're talking illustrative mathematics, which is our text. We're in Unit 1, and we're in the second half, which is about rigid transformations. Today's lesson, number 15, is on symmetry, and specifically it's on reflection symmetry. There's also rotation symmetry. We're talking about reflection symmetry. By the end of the period, you should be able to say, I can describe reflections that take a figure onto itself. So we've studied reflections where you have a line that you're reflecting across. Today we're going to do it where it reflects across itself such that it's going to be the same figure when you reflect it. That's called a line of symmetry as opposed to just a line of reflection. And for the bell work, we had to do some practices. Here's this segment. And there's a video on page 5 where Miss Kirkpatrick explains some more of them. I could say, if I were to do a transformation, let's translate, we have to define the translation. Let's say let's translate this from A to B. And if we do that and apply this translation to this figure, it gets up to here. Now I could rotate this around. This is a different way. These are just different ways that you can get, translate the figure, point B. And we're going to do this 180 degrees. To where it comes back onto itself. So if I apply this second transformation, this rotation around itself, you can see that it ends up back where it started. Let's see, another one that we could do is possibly, she describes doing several of them. One is rotating 180 degrees around the midpoint. We could rotate it 360 degrees around any point. Say I make a point here, and I want to define the transformation as a rotation. So we'll do a rotation, and we're going to rotate around this point at 360 degrees. And I'll do 350 so you can see what happens when I do it 350 degrees. And I'll rotate this figure that much. See, it doesn't quite make it. If I change this to 360, then all of a sudden it's all exactly the same point. And it doesn't matter where this point is. In fact, if I do this at 350, just so you can see how this works, and I move this point around, it moves the idea. If I do it around itself. So if you do any point around 360 degrees around itself, it'll end up with what you started with. And this idea of reflecting and rotating and translating these rigid transformations, these 3 rigid transformations, to get back to where you started from, is in line with what we're talking about today, which is when we have symmetry. Symmetry is when you reflect it. A reflection symmetry is when you reflect an object across a line and it goes to itself. So here, for instance, if it's a rectangle, you reflect it across the midpoints of the sides, it'll reflect onto itself. If I reflect it across the diagonal, a rectangle doesn't do that. It won't reflect it that way. We started off by asking this question: which blue line reflects the line of symmetry for the alien? And some people said they know how to do this, and then they would choose this first one. Notice if it's going to be a line of symmetry, not a line of reflection, because you can reflect anything across the line, but to be a line of symmetry, it's going to divide the figure into 2 equal parts. The only one that does that is this figure right here. For the next several figures, and I'll show you how to do these on this video, but you should try this on your own from pages 9 through 16. There are several objects. I want you to name the object, to define the object, to name or draw the lines of symmetry, all the lines of symmetry, and a description of the line of symmetry, something about what it does, and then give me one non-example. When you do the non-example, I want you to reflect the object across that non-example to show why it is not a line of symmetry. It's a line of reflection, but not a line of symmetry. So, for instance, this is an isosceles trapezoid. It's a trapezoid, but it's an isosceles trapezoid because the 2 legs are congruent. It's a trapezoid because one pair of opposite sides and only one pair of opposite sides is parallel. So it's called an isosceles trapezoid. It is defined as a quadrilateral or a 4-sided polygon with exactly one pair of opposite sides parallel and congruent legs. The only figures that we have that are legs are a right triangle, an isosceles triangle, And a trapezoid can have legs because the two sides that are not parallel are called legs. And here this has one line of symmetry. It's right here. If I were to reflect this point, it's going to go across this line at a perpendicular such that the two segments are congruent. Same with this one. It's going to be perpendicular, and it's going to be these two segments are congruent. This is the line of symmetry. It will reflect onto itself. One that is an example of one that is not a line of symmetry would be this horizontal one. This horizontal is not a line. When you do a line of symmetry, you're going to go equal distance across the line. So I'll go this far to here. I'll go the same distance across this line such that they're perpendicular. And here we go this way, perpendicular to here. And this one's going to go perpendicular to here. So my new figure looks like this. You can see that this is not the same as the original. It is not a line of symmetry. It is a line of reflection, but it's not a line of symmetry. Here we have an equilateral triangle. It is a triangle with all three sides congruent and all three angles are 60 degrees. If I were to draw an altitude, that is a right angle from the vertex, these two sides will be congruent. And I can do that from any vertex. I could draw it where it's perpendicular, and these two sides would be congruent, the same length. And if I do it here, now what do you notice about all these lines of symmetry? What you should notice is that they all intersect at one point. One that is not a line of symmetry on this one could be a line like this. This will reflect across this line at a perpendicular, so it's equal distance on the opposite side. And this one's going to be way down low. It'll be actually much lower than this, but it would look something like this. I'm sorry, like this, way down low. So when you reflect it across this point, it's going to be way down low. Lines of symmetry for a rectangle. A rectangle is a parallelogram, but it's a special parallelogram. It has all four right angles. So it is a quadrilateral with four right angles. And there are two lines of symmetry, here and here. The most common error is to say that a diagonal is a line of symmetry. If I were to reflect this line across this at a perpendicular, equal distance, it'll end up right here. Same with this one, would end up somewhere over here. And what I end up with is this figure. This is a rectangle, but it's going to be rotated. You see, it's going to be different. It's going to be weird. It's not, this diagonal is not a line of symmetry. We have a square. It is a quadrilateral with four right angles and four congruent sides. And this has four lines of symmetry. Of course, we've got the up and down. So if I reflect this across here, it ends up here. I also have the diagonals. If I take this point and I reflect it across this line, it'll end up right there. This will be on itself because it's going to be on a diagonal. So I have the diagonals. Notice all the diagonals, all of the lines of symmetry meet at a single point. And if I did a non-example of this, I could do, say I could draw a line right here. If I do this, when I reflect this across here, it's going to be like this, something like that. It's not going to be symmetrical unless it's right at the midpoints. This is a parallelogram. It is a quadrilateral with both pair of opposite sides parallel. This has no lines of symmetry. A most common error is to say that this line is a line of symmetry. And if I reflect this across here, this will go to here, this point will go to here, this will go to equal distance across this line, and this will go over here. So you end up with something like this, something like that. Not a line of symmetry. The only parallelograms of the line of symmetry are squares and rhombuses, or their children, which is a square, a rectangle, and a rhombus have lines of symmetry. Those are the only parallelograms with lines of symmetry. Here we have a rhombus. It has two lines of symmetry. Notice if I go this way, if I reflect this line perpendicular across it, it ends up at the other vertex. Same if I reflect across this line, this vertex ends up over here. So these are the two lines of symmetry. Ones that is not line of symmetry. If I were to do this with my pen, I'll draw it right here. Now, this will go to the opposite side, to the opposite side, to the opposite side, to the opposite side. I end up with this figure when I reflect it. It's a line of reflection, but it is not a line of symmetry, this orange one. These blue ones are actually lines of symmetry. So they're special. Now, how many do you think there are in a pentagon? Well, there would be 5. Go from the vertex to the midpoint of the opposite side, and I can do this for each of these, and you'll notice that they all intersect at one point, which is going to be that midpoint of the opposites. It's going to be this point right here. All these lines of symmetry. There's 5. If there's a hexagon, there would be 6. You would go from the vertex to the vertex and the midpoint of the side to the midpoint of the side. Here, since there's odd, I'm going to go from a vertex to a midpoint of the side. That would be true for any of these. Circle, this has infinite number of, now my center is not exactly the center, but you can see they're all going to be at the center. This is infinite. So when we look at these, what's true for them? They all intersect at one point. And can you give an example of a shape that intersects at 2 lines of symmetry intersect at 2 points, not the same point? No, it's impossible if they're lines of symmetry. Remember, it's going to divide the shape into equal halves. Okay? What happens if you did a sequence of 2 different reflections across the line of symmetry for the shape that you did today? So for instance, if we did a pentagon, let's just take our regular pentagon like this, something like this, I don't know, something like this, and you were to reflect it across this line of symmetry. If I do that, this vertex will go equidistant, opposite side. This will go equidistant, opposite side. And so we end up with the same figure. Hey, wait a minute. Wait a minute. Lines of symmetry take the figure to itself. So if I did this line of symmetry and I were to reflect, say I reflected this point, it would go equidistant, opposite, perpendicular. These are the same distance. They're perpendicular. This is going to go at a perpendicular. These are 2 at the same distance. Wait a minute, it's going to go to the same point. And whether you do it 15 times across lines of symmetry, you will always end up at the same figure. Here's a summary of what we talked about today. Unless it's a rhombus or rectangle, which is also a square, they have no, parallelograms have no lines of symmetry. Rectangles have 2, rhombuses have 2, squares have 4, and regular pentagon 5, regular hexagon 6, regular heptagon 7, and so forth. Circles have infinite. Diabolic diagonals. This shape is a kite. That's the name of it. It's called a kite. And Kieran thinks that this has 2 lines of symmetry, the red lines, the diagonals. And Tyler thinks there's only 1 line. Tyler is correct. Only this 1 line will divide this into 2 equal shapes. If I were to divide it this way, my shape would go, let me do this in orange, this would be reflected down to here. And when I draw this, the other point would go the other side. It's going to go way up there. These are not the same shape. They are congruent figures because it's a reflection. And rigid motions take figures to themselves, take figures to congruent figures, but it's not a line of symmetry. It's a line of reflection, but not a line of symmetry. This right here is not a line of symmetry. And in the lesson, you can read the lesson summary. I will not read it here. Make sure that you read it. There's sketch 1 with exactly 1 line of symmetry. I'll do that for you right now. We could do an isosceles triangle. It has 1 line of symmetry. You could do a shape with at least 2 sides. What if we did a square? It had 4. Remember, it had this one, it had these 2 that are diagonals. And then we have this figure here. What happens to a rectangle, to the diagonal of a rectangle, when you reflect it across the line of symmetry? So the blue line would become the red line. What does this suggest about the lines of the diagonals of rectangles? And I would like to point out to you that if I were to construct a circle here, rectangles can be inscribed in a circle from their midpoint. That means that all of these are the same. These diagonals are the same. And there's the lesson summary. How did you do today? Good luck, folks, and success.